Okay, I have your exams done. I'll give them to you after class. I have to put the answer key online, which I'll do sometime this morning. Take a look at it. If you have any questions, you can come and see me. I have to put all of the scores. I have them like all download and stuff from Top Hat. I have to put all those online, which I will do hopefully today. So when I release those, it'll bring your score up to date, at least to where the syllabus lines are. Although those may go down at the end of the semester. So it'll give you a general idea of where you're at. And if you're concerned about that, you can come and see me. There's some dropping that will happen, like we've only had 4 in-class quizzes, and I think I said I would drop 2. I dropped 2. So if that means that everybody gets close to 100%, then next semester we'll have more. We'll have a lot more in-class quizzes. But at this point, we may have 1 this week. We'll see how it goes. What we're going to do is we're going to finish up chapter 12 this week, and then on Canvas, I've laid out, I think, the reading assignments from the Top Hat. I did put chapter 12 problems as due on Sunday at, 11:59.
Is there supposed to be end of chapter questions to check if those didn't show up?
I'll take a look at it and see.
Do we still have to do the resume, like turn the resume?
Yeah, let me talk to you on Wednesday about the resume thing, because if you got your resume done, that's fine. They were supposed to have put everybody in a Canvas class for the CAS Professional Development Program, but apparently they're running behind on that. So I think if you're like probably a junior or senior, you may already see the Canvas site show up. Some of you have done resumes last year for various programs. So if you've got it done, that's fine. If not, then I may end up having that done next semester. Because they just told me the other day, oh, well, we're running behind on getting people into Canvas sites. And each department's supposed to have their own criteria for what workshops, so it used to be you had to go to a workshop to get your resume, to learn how to do the resume and then have it approved so I could go up onto Handshake or whatever that thing is called. They haven't done a workshop because it's an online thing now, but it's only online if you have access to the Canvas site, which, again, they're running behind on. So I may end up giving people credit. If you've already done, I'll keep track of that, and then next semester we'll probably have a couple of those things. So let me see, because I have to talk to the people in career services and see exactly what's going on. But if you've already had it done, then don't worry about it. If you haven't, let me see, because I figured that the last week people would be scrambling to do that anyway, because, I don't get things done 3 weeks before a deadline unless I need to. So that's just the way we work, but they may not be able to handle it over there. And yet they've been saying, oh, well, look, he hasn't put it in his class, so that means everybody has to do it. So I'll figure it out by Wednesday. There's also course evaluations. I don't know if you have or you will receive an email. Okay, that's going to be like an automated Canvas email about going in and doing course evaluations this week and next week. We'll talk about that on Wednesday as well, because there's a different system that we're starting to use. If you're used to just having somebody hand out paper, that's not happening. The last day of class, we're not doing course evaluations. They'll be online for you to be able to do. But we've changed over systems, so if you get an email, that's the email for the course evaluations. So I have to see where that stands as well. Ashley, you have a question?
I was just wondering if it was, because I have access to the Canvas site. Is it all online now? You don't have to go to a workshop?
Right. So if you have access to the Canvas site, every workshop has a certain component online, that an online tutorial you can do. So so for the CA has professional development, which I'm not sure if you guys are up to speed on that. It's a mini version of Bowler, of the Bowler professional development. Each department is supposed to have a series of workshops that you're supposed to do, as well as then a whole bunch of optional things. So like in chemistry, we have 5 workshops that you have to do by graduation to get credit for that, as well as 2 optional things. And you can start on them as early as your freshman year, but it used to be that you had to do the workshop on it, and now there's an online version. So the idea is you when you have a resume approved and up in the handshake, you've completed that task. So just so you know, for next semester, I'm probably going to ask for this class, and I'm going to talk to Dr. Kwan about requiring it for his class too, LinkedIn, and also having a LinkedIn profile. And you may say, LinkedIn, because I don't quite get LinkedIn either. But it is kind of useful. We do have alumni that have gotten jobs because they've been on LinkedIn. They go from job to job because they get better offers all the time. I wish that would happen to me, but it's not likely. So they have their LinkedIn profile. From a chair standpoint, this helps me keep track of where our alumni and our current students are doing internships. Because if you keep your LinkedIn up to date, then I'll know where chemistry majors have internships this coming summer. At the end of summer, I'll know where their internships are. When they get a job, I'll know where their job is. I'll know. So it kind of helps us keep track of people that way, because there's no other mechanism I have other than a couple faculty members' Facebook pages, because they're friends with everybody, one faculty in particular. But so I'll probably ask for that in a cover letter, because those of you that are sophomores, you're going to want to have your cover letter and your resume done about midterm next semester, so you can start applying for internships. And that includes stuff at the clinic too. So that's why I kind of made it part of this class, was to get people thinking about their resume and then keeping it up to date, as well as the cover letter. And Dr. Lee's going to have something for pre-health and biology. I think they're making it a graduation requirement. We haven't gone that far in chemistry to say it's required or you don't graduate, because I don't want to be in that. I don't want to be in that position to say, oh, you're not going to graduate because you didn't have a resume done, or the other ones. But it's a good thing. And there's very few things that as a university we're like sort of riding the wave instead of being swamped by the wave that we're ahead of. But this stuff we're ahead of, particularly in Bowler they are, but we can't really replicate that with with 60% of the students. So that's what'll happen with that. But I'll give you more information specifically. If you're done if you have your resume, if it's up on Handshake, if it's been approved, or you have an appointment to make it approved, great. Then go ahead and follow through on that. And if not, we'll see what we can do, and then I'll make that part of the requirement for next semester. So if you're already done, you're done with that part for next semester, and then if not, then you can just work on that. If it's on Canvas, you can work on it even over break. What else? Course evaluations are coming. Final exam, in the last folder on Canvas, and one of the things I'm going to have to do for next semester is to integrate Canvas and the Top Hat book better. There are review questions for the final exam, and I went ahead and released those. I didn't release the answer key. And so you have access to that. That's about 60, 70 questions or so of my writing. Now there's free radical halogenation, which is not on there, and there's naming, which is not on there. So I'll have to think of some naming questions to maybe put on there to help you review that part for the final. But everything else, there's those questions, and then I'll go ahead and release the answer key later on in the week. So there is some more practice. There is in the library. There's an ACS study guide. This semester is not an ACS exam. It's an exam that I've written, but it will be multiple choice. So if you want more multiple choice questions to work on, there are ACS study guides in the library on 2-hour reserve, and they are organized according to topics, so that SN1, SN2, E1, E2 are all in one chapter, as would be alkene additions. So you could use those as supplementary practice problems as well. So there's a lot of practice problems, including going back through your older exams, as well as going and looking at some of the top hat questions. But that's where, and our final is sometime next week. Whatever it is in the syllabus, that's what it is. I'm not going to venture a guess because I haven't gotten that.
Friday.
Is it Friday? Okay. So we'll finish up completely chapter 12, which is why I pushed the date to Sunday, although it could probably go into next week. But it depends on when the other class's final is. It could be Monday. I have a suspicion it might be either Monday or Wednesday. Okay, so that's where everything is at on Canvas. I think I have one more practice problem set that I can go ahead and put on. And we use part of Friday as review, but we have topics that we need that we'll go over, and I haven't placed any videos in here because I have to find them. But I'm just going to be lecturing what would normally be on the video. Okay. All right. Any questions? That's kind of rambling, but okay. We have a couple topics that I'd like to talk about today. And going back here, we have Oxymercuration-Demercuration, and then also Anti-Markovnikov addition of HBr. And then there's this kind of, there's one more addition reaction on Wednesday, and then there's a couple of alkene reactions that are that's slightly different. So we're still into addition reactions. So we've got, I think, 3 more entries to put into that table. And so we'll talk about these along with where they fit in terms of regio and stereo selectivity. So let's talk about mercuration-demercuration. So mercuration-demercuration should have gone with alcohols, should have gone in the synthesis of alcohols. To review, remember, if you want to take an alkene and you want to convert it to an alcohol, you have 2 methods to do that. Right? We could use H plus H2O, which would add an H and an OH across the double bond. It would add the H and the OH Markovnikov, and it would be 50-50 cis and trans, because it undergoes a carbocation intermediate. So that's method number 1 that we can use to convert a double bond into an alcohol. The second method was hydroboration oxidation, which is an Anti-Markovnikov addition. And if you remember, that was 100% cis. So those are our two previous methods. So we can add Markovnikov and Anti-Markovnikov. So the third method is going to allow us to add the H and the OH Markovnikov with 100% trans stereochemistry. So we're almost to having the four possibilities. Having it 100% Markovnikov cis, 100% Markovnikov trans, and then having the two antis would give us the entire complement. But we don't quite get to all of that, which means we're going to have to use some other methods. This involves using mercury acetate, and the way it's abbreviated is HgOAc. So this is actually a mercury 2+ ion along with an acetate, which is the acetic acid, which is the 2-carbon acid, deprotonated, which makes it called an acetate. So mercury acetate has 2 -1 counter ions for the mercury 2+ ion. And so this is what we first add to the double bond is mercury acetate. Now, if you think about the way mercury acetate is going to react, this is going to look exactly like a bromonium ion. And normally, if I would have not been sort of freewheeling in that lecture, I would have gone bromonium ion, then mercury acetate. Or actually would have gone mercury acetate first. So all the characteristics of the bromonium ion reaction are going to be true for this. So what would happen then is we're going to take our double bond and we're going to add to that the mercury, and it's got 2 acetates attached to it. So if I'm moving arrows, I would take this arrow to bond to the mercury, and then one of the acetates leaves. So what I'm going to have is I'm going to have the double bond, and it's going to be partially bonded to the mercury ion then with just 1 acetate on it. So this mercury acetate has a net charge of +1, and the mercury is big enough to sit over both of the carbons. So this is very much like a bromonium ion. It's not very much, it's exactly like a bromonium ion. So the mercury is big enough to sit over both the carbons. It has a +1 charge. And so what it's going to do is it's going to transfer some of that charge so that now the carbons have some delta positive charge as well. So I'm delocalizing the +1 charge. Now mercury is a little different than bromine. Bromine doesn't like a +1 charge at all, so it just transfers all of its +1 to the carbons. But mercury could have a little bit. So really there'd be a kind of delta positive charge over all 3 atoms in the triangle. Okay. So once mercury then is a triangular intermediate, we're back to bromine, or we're back to a bromonium ion. So the second step of this reaction then is going to be to add H2O. And so I'm going to add H2O, and which carbon is the water going to attack? From underneath. Because it's a triangular intermediate, the water's going to have to add underneath. That sets 100% trans stereochemistry. But which carbon is the water going to add to? The carbon that is most substituted. because that's the carbon with the greatest delta positive charge. So the water's going to add to the carbon that's most substituted, because that's the one with the greatest delta positive charge. And it's going to add 100% trans because of the triangular intermediate. So that means that, and in this case, whenever I've done all these addition reactions, I've just given you a generic alkane. I haven't been specific. But if I want to go back here, let's just put 2 R groups here and 2 H's here, and then 2 R groups here and 2 H's here, so I can be specific in terms of the regioselectivity of the reaction. So that means that the water's going to add on the carbon to the left because it's most substituted, and then the mercury is going to break its bond and move over to the carbon. So that means that I'm going to have my oxonium ion down here, along with my carbon with its 2 alkyl groups, and then over here I'm going to have the mercury attached to that carbon. So that's going to give me that molecule, and then my pair of electrons move so that I now lose my H+. And so my initial molecule that I make has the addition of the mercury acetate and the OH, 100% trans. If I treat the mercury acetate +1, if I treat that as if it was an H+, what I have is Markovnikov addition. So for this mechanism, if you went back and you erased the mercury and you put in bromine for the bromonium ion, you would have this mechanism. So it's exactly the same. Okay. So it's Markovnikov because I'm saying the electrophile adds to the carbon with the most hydrogens. Okay. All right. Is everybody okay with that? So the problem here is that's not H and OH. That's OH and mercury. So how do I get rid of the mercury? And it'd be best to get rid of the mercury and put a hydrogen in exactly the same spot as the mercury. So the first step is adding mercury acetate and water to the double bond. The second step of this mechanism is going to be to remove the mercury and put a hydrogen there. So let me rewrite. I'm just going to rewrite the structure that I'm starting with here. So that part of the mechanism is exactly like bromonium ions. We can understand that. The next step, we're going to just say this happens, and it's going to be like BH3H2O2. I'm not going to hold you responsible for this mechanism. But now what I'm going to add to this is I'm going to add NaBH4, which is called sodium borohydride. And so we know that the sodium is +1. Sodium, potassium, they're all counter ions. Right? When they show up in the book, you kind of ignore them, and we're just working with the negatively charged species. Right? So if I'm adding NaBr to something, I'm really adding Br- to it. So sodium borohydride, what's really important is the BH4 minus. So in the BH4 minus, we've got 4 hydrogens attached to the boron. Now boron is less electronegative than hydrogen is, so that puts each one of these hydrogens with a delta minus charge and the boron with a delta positive charge. That's why this is called borohydride, because a hydride ion is an H minus. So sodium borohydride is essentially an H minus. So what happens is, for this reaction to be 100% trans and Markovnikov, the hydride comes in and replaces the mercury in exactly the same position that the mercury was in. So that when we add the sodium borohydride, we end up with the molecule where the H now has been added, has substituted for the mercury. So now I've added H and OH, 100% trans and Markovnikov. But it took me 2 steps. Okay, so this step of reacting hydride with the mercury is not an organic step, it's an inorganic step, and so we're going to ignore it. We're going to say it's beyond the scope of what we're interested in. Okay. But that's what happens. If the hydride didn't replace the mercury in exactly the same position, we wouldn't get 100% trans addition. Okay, so it's a two-step mechanism. Mercury acetate and water, then sodium borohydride. Okay. So I'm showing you the mercury acetate addition, relating it to the bromonium ion because it's a triangular intermediate, which makes it 100% trans. And because it's like the bromonium ion, and the mercury goes to the carbon with the most hydrogens, it's Markovnikov. Okay. Now, as far as this being a useful reaction, it may be useful in academic labs in terms of adding H and OH 100% trans across the double bond. It would not be very useful in the pharmaceutical industry. Mercury is a neurotoxin. There was a day when people used to play with it. You'd have it in thermometers and people would play with it. Those days are over. We don't have mercury. Well, we do. I have some mercury thermometers, but we'd have to evacuate the building if they ever broke, because mercury is a neurotoxin. And that means the mercury compounds are usually not very good. You can go into the whole mercury allegedly, not allegedly involved in autism. I'm not going to get into that argument. But there was a time when a mercury compound was used as a preservative in certain vaccines. That's where that whole thing comes from. You shouldn't vaccinate your kids, which is probably extremely poor advice from a public health standpoint, unless you believe celebrities that have their doctorate or have their MD degree on the side. So you can research that yourself. But that's where that whole issue of mercury in vaccines came from. It was really in there as a preservative. It's been removed, I think, for many, many, many years. So making compounds with mercury in a pharmaceutical sense would not be good. The FDA would basically make you show that every atom of mercury has been removed from that molecule, which you really can't do. I mean, you can detect mercury using some instrumentation, probably down to a number of atoms, but not every single atom. So this would not be used in a pharmaceutical sense. whenever I talk about mercury, we have to talk about Alice in Wonderland. Not from the standpoint of Alice going through the mirror, because then all of her enantiomers would be inverted. So I don't know what she'd eat, because all the stuff that she would normally eat's now been have their chiral centers inverted. So it'd be hard to tell what exactly she would be eating and metabolizing. But also the idea that the Mad Hatter was mad. He wasn't really angry. He was suffering from neurological disease, because in the old days they used to make the hats stiff by using mercury on the leather. So hatters were mad because they used a lot of mercury with their hands, and so they ended up with that neurological disease. So mercury not really going to be used in a pharmaceutical sense. For that reason, and that's true for any heavy metal. We'll talk about chromium and some other metals in the future. They may work well for us, and even then it would not make a good green, environmentally friendly lab here. Okay, so let's talk about regio and stereoselectivity. So the way this reaction would be set up would be, we would take our alkene. Number one step would be mercury acetate, H2O. Second step would be NaBH4. So this is the way you would see the reaction written in either the book or if I was to write it. Okay. So we know that we have to add H and OH, 100% trans, Anti-Markovnikov. So all of our rules for regio and stereoselectivity are in play. For instance, for this molecule, what I would say is, okay, I've got my CH3, I'm going to add my H and my OH Markovnikov. They're going to be trans, so that they have to go on the opposite wedges, and then the methyl group would go on whatever wedge is left over. So this would be the major product of this reaction. So what would this reaction be? Regio or stereo? Or both? Or neither? Let's take regio first. Is this reaction regioselective? Yes or no? I see some heads nodding yes. Right. If I added the H and the OH anti-Markovnikov, would I get a different product? Yes. Did I select one over the other? Yes. Stereoselective? No. Why? Because even though this reaction is 100% trans, when I added the H and the OH, did I make a chiral center? No. There's no chiral center in that molecule. Or no, sorry, there's not. Well, no. There is no chiral center in that molecule. But I need two chiral centers in order for it to be stereoselective, right? So this reaction would be regio only. If I wanted to make it stereoselective, what I would do is say, okay, now let's do that same reaction with a dimethyl cyclohexane. And so if I did that, then I would have my two methyl groups. I would add my H and my OH, but now that I made the molecule symmetrical, or better yet, each of these two carbons has 0 hydrogens, so therefore there is no Markovnikov or anti-Markovnikov product. The H and the OH would still add trans. Now have I made two chiral centers in my product? Yes. Did I select 100% trans or 100% cis? Yes. So this reaction would be stereoselective, but because the original molecule was symmetrical, and there is no anti-Markovnikov or Markovnikov product, it would not be regio. Okay. So we're following the same set of rules that we did before. And there's one problem set where now you could go and you could do all 4 of the cyclohexanes now with this reagent. Okay. All right. So mercuration-demercuration allows us to add Markovnikov, HOH Markovnikov 100% trans, if I needed to. All right, is everybody kind of okay with that? So the other reaction that we can do is to add HBr with a peroxide. So hydrogen peroxide is H2O2. That's hydrogen peroxide. And when I put 2 alkyl groups on the hydrogen peroxide, I make just what's called a peroxide, an organic peroxide. Now, when I add HBr in the presence of a peroxide, the mechanism is going to change, which means that the stereo or the regioselectivity is going to change. And this mechanism is going to be a free radical mechanism. Now, normally we would have gone over free radical mechanism, so I would just say, oh, here's the free radical mechanism, and you've already seen these steps before. Unfortunately, you haven't, so this is where we're going to talk about radicals for the first time. And so what is a radical? Well, for the most part, radicals are unstable. That may hold true in real life as well. Depends on the radical. But a radical means that an atom has an unpaired electron. That's what a radical is. And if it has an unpaired electron, it cannot follow the octet rule, because odd will never equal even. So when you have an unpaired electron on a species, that is called a radical, and it's called a free radical, I guess, because it is free to roam around wherever it is. We have lots of free radicals in our body. For the most part, they are bad, and we have mechanisms to kill them before they do various bad things. So an unpaired electron then on a carbon makes that carbon not have an octet. But fortunately, we've talked about the stability of carbocations. And the problem with the carbocation is that we only had 6 shared electrons, so the carbocations are worse, in worse shape than radicals are, because at least radicals have 7. When we talk about free radicals, tertiary radicals are more stable than secondaries, which are more stable than primaries in terms of stability. For free radicals with carbon, there is no prohibition. There's no rule saying you can never write a primary radical. You can. Primary radicals form because there's 7 electrons as opposed to 6. They're not that unstable. But a primary radical is less stable than a secondary and a tertiary. For the same rules that we talked about before. You have a carbon. Every alkyl group you put on there, the carbons are slightly negative because they've taken electron density from the hydrogens. They now can push a little bit of electron density into that radical. That radical, all it's got to do is get from 7 closer to 8. With a carbocation, it's 6. That's a much more difficult task. So tertiary radicals, more stable than secondary, more stable than primary. Now the reason I bring up these radicals is because this mechanism now goes from a carbocation-based mechanism to a free radical-based mechanism. So here's what happens. In the first step of this mechanism, the organic peroxide cleaves at the oxygen-oxygen bond. So what I do is I cleave that bond, and since those two oxygens have the same electronegativity, there's no reason why one should get both and the other should get none. They have the same electronegativity, so each oxygen's going to get an electron. So that's going to make two alkoxy radicals. And so this can occur by light, or it could occur by heat. But that's the first step in this mechanism, is to break the peroxide apart and make these peroxy radicals. Now the second step in this mechanism then is for a peroxy radical, or an alkoxy radical now, to react with the double bond. Next step is for it to react with HBr. Now radicals love to what is called abstract hydrogens. That's what radicals do. Radicals come in and they take a hydrogen atom from molecules. And so the alkoxy radical then, this hydrogen-bromine bond will break, only instead of breaking heterolytically, where the Br becomes Br minus, the A and the H becomes H plus, each atom gets an electron. And so what happens is the H dot pairs up with the RO dot. So we end up forming an alcohol and a Br dot, which the Br dot is nothing more than a bromine atom, a neutral bromine atom. Okay. So once I form the alkoxy radical, it's going to react with HBr and it's going to form a bromine atom, which has an unpaired electron. So then it's the bromine atom that's now going to add to the double bond. So now I've got a Br dot, and I'm going to use my two hydrogens here. I'm going to use two R groups on one carbon, two hydrogens on the other, and if I think about breaking the carbon-carbon bond and giving each carbon an electron, the bromine is going to pair up with the carbon to give me the most stable carbon radical. So there's two possibilities here. I could add the bromine to the left-hand carbon, which would make that primary radical, or I can pair up the bromine with the carbon with the two hydrogens on it, and I can make a tertiary radical. And so the bromine is going to add to the carbon on the right because it wants to make the most stable radical. Okay, and so this is going to be the major product. So what's happened? Normally the Br would add to the carbon that's most substituted. What's happened now because of the change in mechanism the bromines added to the carbon with the most hydrogens. So now I've made an anti-Markovnikov addition. What happens in the final step? In a final step, the carbon radical reacts with another HBr molecule. So what happens is that we break apart another HBr molecule, and now that H gets attached to the carbon that was in the double bond. And I make another Br atom. So we'll finish this up a little bit on, we'll finish this up on Wednesday, but whenever you have a carbon radical, it tends to generate another radical, another atom. So this process, if I made just one RO dot, you can see that every time that reacts, I end up with another species with an unpaired electron. And this is the problem with radicals. Once you form one radical, it continually perpetuates new ones until you run out of stuff. So the problem in our bodies is if we get one radical in there, it's going to run around, it's going to try and abstract hydrogens from things that we don't want it to abstract hydrogens from. Like I don't want it abstracting hydrogens from my DNA. Unless it's going to somehow mutate me and give me superpowers, good superpowers, I don't want things running around getting mutated. So we have to have systems in our bodies that will take these free radicals and will basically make them react, but then the other species that's formed just sits there. It doesn't try and take away another hydrogen. So this is why HBr peroxide is anti-Markovnikov. And we'll talk about the structure real briefly on Wednesday. The structure of a radical is exactly similar to a carbocation. Okay. So we'll finish this up.